Hello everyone, welcome back to another video on Piston Door Terminologies. Today we're going to talk about door patterns, and this is part one. Hopefully there will be part two and part three. I cannot guarantee, but then yeah, either way. Hopefully after I work on more stuff, then I can release part two and part three because there are quite a bit to talk about for door patterns. And this is taken as of 22nd September 2024. Now, before we start on this video, if you are really interested in going through all of the video content, you should download this document, the door pattern definition documents that I basically wrote. This is version 2. This is also provided in the description below. So this basically provides mathematical definitions for several door patterns and is highly referenced in this video. So yeah, and the reason why I need to write a separate document for it is because the regulations document, quite frankly, lacks the definitions of multiple door patterns. It can really only give an example of door patterns, and some of it doesn't even give any examples at all. So if you really want to know the definition of terminologies in here, door patterns, you do need to use some mathematical definitions to describe it rigorously. So here I just wrote documents in it, so hopefully people who know mathematics will understand, and people who don't, I hope this video helps you because I'll explain to you. And notice that the document is subject to future updates, and because the document is highly technical, yeah, I'll give an explanation, which is what this video does, and hopefully you get an understanding of it. So yeah, so make sure you download it if you are interested in the terminologies. Otherwise, you just skip this part. But yeah, either way. So yeah, I'll move on. Now, the first part doesn't relate to any of the documents that I wrote. It's just talk about how we configure door sizes. So we take from the regulations documents, section 2.1 part A. So here it says size is the minimal set of dimensions that can describe the type size inside of the door frame. And it can have four forms, M by N by K, where M is the width, N is the height, and K is the depth. And then the second one is M by N. So M is the width and it's the height, so you can just apply that. The third one is M wide, the fourth one is N high. Now, the important thing isn't the forms, the four forms of it, is that size is the minimal set of dimensions. So here, the gray text gives you a good example. The 16 by 16 funnel door minimally describes the funnel size, even though its door blocks stretch 16 by 16 by 8 in all three dimensions. So because 16 by 16 by 8, the depth of the funnel pattern, it has 8 blocks. But then by saying 16 by 16, you already know the depth of the funnel door has 8 blocks. So you don't need to describe the depth, and nobody says 16 by 16 by 8 funnel door. That's weird. So yeah, we try to minimalize how we describe doors, basically. And then we use these four forms to describe it. And now, in the later part of the video, I'm going to talk M by N by K with M by N by L. That's because it's quite troublesome if we miss out K, because mathematically we like to use Asdjke. But then here, if it occupies M and K, then I cannot use Asdjke, basically. So I'll replace M and K with M and L. So M by N by L for indexing convenience. So yeah, so that's the context. I'll also repeat the sentence a bit later. Either way, so this part is not that difficult to understand. So, but I will still give you some examples. So, the first form M by N by K, we can have 5 by 5 by 2 piston door. Now notice if it's a 5 by 5 by 1 piston door, we won't say 5 by 5 by 1. We only say 5 by 5. So unless the depth of your door is larger than 1, then you will include the K index. Otherwise, you just say 5 by 5 piston door. You won't say 5 by 5 by 1. But then here, since K is bigger than 1, then we say 5 by 5 by 2 piston door. So yeah, that's the important thing to know. The second one, as already shown in the previous example, we don't say 16 by 16 by 8 funnel door, we say 16 by 16 funnel door. So here, we won't say 3 by 3 by 2 funnel door, we only say 3 by 3 funnel door. The third example is 3 wide expandable door. Now, when you see M wide and N high, you can relate to a few things. They usually describe either expandable doors or doors that have exotic door patterns and hallways. And the fourth one gives you just the example for that. 3 high triangle door. A triangle door doesn't have the rectangular pattern. It doesn't have the rectangular hallway. It uses a triangular hallway. So it doesn't really make sense to say, 3 by 2 triangle door. Because it isn't rectangular. So if you're trying to say, something 3 by 2, you make people think of the rectangular hallway, when in fact, it's just, a non-rectangular hallway. So, yeah. And also I should say 5 by 3 triangle door if I'm relating to the 3 high triangle door. But either way. So, the thing is, if it uses a non-rectangular hallway, chances are it's going to be described by M wide or N high. It usually is N high, it's not M wide. We seldom use M wide to describe patterns, to be honest. It's usually just on expandable doors, but then either way. So just remember that. And for exotic door patterns, you can think of examples like triangle, circle, or diamond. Although some people will still call diamond as M by N, but for N high is also acceptable. So yeah, either way. So that's that. So hopefully the discussion on door sizes here help you understand more on how we name our door sizes. So yeah. So now we move on to the main part of the video, which is door type. But first I want to outline it first, because there are 4 parts of door types that I can talk of, but then it'll be too long. So I'm just going to select some things that I want to talk about. And I have the resource to talk about, I guess. So from section 2.1b, there are 4 sections. First is the arrangement of the door blocks. Second one is the composition of the door blocks. Third one is the arrangement of the hallway. And fourth one, guess what, is the composition of the hallway. So yeah, 2 arrangements, 2 compositions, 2 door blocks, 2 hallways. Combine them together, you have 4 combinations, and that's that. There are 4 sections in this section 2.1b. Now, by looking at the names of the section, it doesn't really give you an intuitive explanation of what the sections are going to talk about, really. It's actually rather a bit confusing, at least to me, I guess. So here I give you some renames of it, and hopefully you will understand what the sections are really talking about without looking at the details of what a section is talking about. So for the first section, arrangement of door blocks, you can think of it as door pattern and transformations. So door pattern, it really lists out the door patterns that we currently accept, and then transformations of the door patterns. And compared to the second section, we say that it is talking about door pattern modifications and door block choices. Now, what is the difference between transformations and modifications? While transformations are one type of modifications, what's different of transformations is that it doesn't alter the door pattern itself. It only relates to, rotating the door pattern or flipping the door pattern. It doesn't really change the looks of the door pattern. Versus modification, it can really change the door pattern looks of it. So that's the difference between transformations and modifications. Although transformations are a type of modifications, it only describes a certain subset of modifications. So, yeah. So that's the difference. And for the arrangement of a hallway, I can, describe you as the shape of the hallway. The shapes of the hallway are listed in this section. And then the composition of a hallway, well, if we have door block choices mentioned in the composition of door blocks, we also have hallway block choices mentioned in the composition of the hallway, and this gives the regulations of it. So yeah, so that's basically the outline of how door type is regulated in section 2.1b. But then in this video, I'm not going to talk about all of them. I'm going to talk about these two sections. So yeah, and then furthermore, let's just introduce you to these two topics. So arrangement of door blocks, so it's the first section. This is going to be our main focus. And the video will cover basically everything except two: staircase and dual transformation. The reason why I'm not going to cover staircase is because it's a bit weird. It's not really like any other normal door patterns. It's just not fitting to talk about staircase in this video. And then for dual, although the definition is actually quite clear here, but then I cannot find a satisfying mathematical definition that can describe how I can make a door pattern to be of the dual transformation. Although here you can also see what it's trying to describe, but not in a mathematical context. So it says the type is mirrored to look the same from the both sides of the hallway with both sides overlapping at least one block. So basically you just mirror a door pattern from the front to the back. So, both sides look at it, it's the same. And then you also have to make sure that it has the least amount of overlapping blocks, I would say, for regulatory standards, I guess. So yeah, so that is why I'm not going to talk about the dual pattern. I haven't found a mathematical definition that I can describe it with confidence, although I have a general idea. So yeah, and I guess here I should also mention a key thing is that we say a funnel pattern, but then if it is a dual funnel, then we say it's a vault. So please notice that this is quite substantially different from what you're going to find in YouTube video titles. So we don't say a 3x3 vault door, we say a 3x3 funnel door. Usually people don't even do much of vault doors. What they are really doing are funnel doors. So yeah, you have to reconcile between what the YouTube video titles are and versus the regulatory standards of the documents here. So here we are using funnel instead of vaults. So vault is describing dual funnel. So please notice that. So yeah. So that is the arrangement of the door blocks. And now we're going to talk about the outline of the composition of door blocks. So it's the second section. Now there are a lot of them, but then I'm going to cover only three: Sissy Bar, Checkerboard, and full checkerboard. And the important thing is under regular arrangement. Regular arrangement is in here. So what is regular arrangement? Well, basically, I'll also describe it a bit later, but basically just a flat layer of door blocks. And it's important to mention that it's under regular arrangement, because if it's not regular arrangement, then it can explode to more door patterns that I have to describe. So yeah, it's going to be only under regular arrangement, and probably also because people really only do these three door patterns under the regular arrangement. They don't really do it in other arrangements. At least it's not that well defined, I guess. So yeah. So that's why I'm just going to talk about those under regular arrangements. And yeah, and also another thing that you can see is that there's no full checkerboard here. There's only checkerboard here. That's something that the document basically misses, but then we do really have full checkerboard as a valid door pattern, I guess, under common practices. So yeah, that's why I'm also going to cover them, even though the documents doesn't really officially include it. So it's important that we also know the differences between the actual documents and our common practices. So yeah, that's also something that I'm going to cover throughout the entire series. So yeah. So that's that. And now I'm going to switch over to another presentation which it allows me to write mathematical stuff more beautifully instead of using, the standard PowerPoint formats. So let's go to there. Okay, so I've also used start mode in this slideshow. Yes, so and the ratio of the slides are a bit different, but so yeah, get used to it, hopefully. So I'm going to, for section 2, highlight some important definitions, so the wordings of it, and then give you some context of what's going to happen there. So I don't expect you to read the entire definition of different objects because it can be quite confusing to many of you who doesn't have a strong mathematical background. So here I'm just going to mention some specifics of it. So definition 2.1 is about matrices. So a matrix, plural, matrices, is a rectangular array of numbers. So that's all you need to know. But then the question is, why do we need to define matrices? What use does it have? And here I'm going to tell you, in this document, what the matrix does is basically representing one layer of the door pattern. I don't define what layer is in here because, yeah, it's just not worth it. So either way, just imagine every single door pattern has layers of it, and each layer is just, well, the number of layers is just the depth of the door pattern if you really want to relate to it. So, and each layer represents one depth of the door pattern. So yeah, hopefully that convinces you. So now we're going to move on from matrices to third order tensors, which should be very unfamiliar. But essentially, third order tensors are just, or I should say tensors, are just generalizations of matrices, because you can just generalize matrix to higher orders. But here we're just going to use third order tensors. So the definition of a third order tensor, or plural third order tensors, is an array of matrices. Because we're just talking about third order, so just adding one dimension, basically. But then why do we need this definition? Now, in this document, we are going to represent door patterns with third order tensors. Because what third order tensors does is that it can represent all layers of the door pattern in a single object. And it's important that we use a single object to describe a door pattern. We don't want to use multiple objects to describe a door pattern. It doesn't work that well. So either way, so we define basically an object that can help us to explain door patterns or represent door patterns. So yeah. The second part I want to highlight is the size of the third order tensor. So we say the size of the third order tensor as an n1 by n2 by n3 tensor. And what does it mean? It's a third order tensor with n3 matrices of size n1 times n2. And then the second part is the context of it. So you have to notice that n3 is talking about the number of matrices that we are including in this single mathematical object. And then each matrix has a size n1 times n2. And the rows are counted from the top, columns counted from the left, matrices are counted in ascending order. And the last part, matrices are counted in ascending order, isn't really as intuitive as you might think. So I'm going to explain it. So what do we mean by counting in ascending order? It doesn't really make much sense. You can imagine the matrices are counted from front to back, basically. And the matrices are the layers of the third order tensor. Again, not going to define what layers are, but then just imagine that, n by k is the depth, how many layers do you have? You have k layers, basically. And layers basically just corresponding to depth. So yeah, so that's that. And then another thing that I want to note is that, the top left front entry is 111, while the bottom right back entry is N1, N2, N3. So yeah, that's important. In case if you really want to know, the top right front entry and the bottom left back entry, you can refer back to the definition of matrix, and then depending on the size, then you can write that out. And in the documents, there's also a graphical depiction of what a matrix looks like and how we index those numbers. So yeah. So hopefully you would understand these. And then the third part I want to mention about definition 3.1 is a Doyle pattern of size m by n by l is represented by an n by m by l third order tensor. There are already two subtle things I want you to notice. The first one is that, as I've already mentioned, the regulation document describes size with m by n by k, but then we use m by n by l. So k replaced with l. That's the first important thing. The second one is the positions m and n are swapped due to the definition of matrices. Now, if we remember, in door sizes, we say m by n. And m is the length, or I think in the document it says the width. N is the height. But then, if you refer back to the definition of matrices, definition 2.1, what it says is basically, m by n. How do I say? So door patterns, you have m as the length, so you have m columns and n rows. But then if you refer back to the definition 2.1, you would see it's swapped. We should say, m columns and n rows, and the matrix, we call it n by m. So for the third order tensor, it will be naturally n by m by l. So yeah, the unfortunate thing is that we do have to reconcile, between how we say door patterns and how we use matrices to describe it, and hence third order tensors. So if we're using the standard definition of matrices, then we will have an index swapping. So this is unfortunate, but then yeah, just pointing this out, and hopefully you'll get used to it. So yeah, that's that. And also, for the third order tensors, they have entries like I previously said, 111, n1, n2, n3. But then, what does those actually mean in the Minecraft world? I don't really set much of it in definition 3.1. In fact, I said I'm going to omit it. Now, if you really want a visualization of it, you can think of the Asdjke entry representing an arbitrary Minecraft coordinates, which is, for example, x plus j, y minus I, z plus k. The reason for minus I is, well, the matrices go from 1 to n, but then in the Minecraft world, if you go like this, you actually reverse in terms of the height, because I from 1 to n is going from top to down, but then in the Minecraft world, for the y-axis, from smaller number to a larger number, it's going from bottom to up. So we have to reverse it, so negative it is. And then you can just plug in any values of x, y, z, basically. And now notice another thing is that it's not x plus I, y minus j, z plus k, because we have to swap m and n. Naturally, for the entries, we also have to swap So I really represents the y-axis. J really represents the x-axis. So make sure you know this well. See, or otherwise you get very confused with how the entries are going to be named afterwards. So just swap between the first and the second entry if you really want to depict it as an x, y, z axis. So yeah, there you go. And then another thing about definition 3.1 is the role that we are going to do the representation, where the value 1 represents block presence and the value 0 represents block absence. So that's the role that we're going to talk about. And there's really nothing special about the following two definitions, but then it's important for me to also tell you so that you get the context of it, because I cannot guarantee that you're going to look at the document. So definition 3.2 is the indicator function. So for any statement E, define the indicator function of E. Basically, it's just the indicator function E is true. Now, this is a case-defined function. And if E is true, then the indicator function gives you 1. But then if E is false, it can only be true or false, then the indicator function gives you 0. So yeah, that's what an indicator is, basically. If it's true, it gives you 1. If it's false, it gives you 0. So, there you go. Nothing special here. And then definition 3.3 is the minimum and maximum functions. So for any, real values, x1, x2, define x1, a little hat thingy, x2, and then a little hat thingy, several dots. It's just the minimum of x1, x2, blah, blah, blah. And then for the maximum, it's just the reverse. It's instead of using like a hat thing, we use a v, basically. x1, v, x2, v, blah, blah, blah. It's just the maximum of x1, x2, blah, blah, blah. So yeah, so there you go. So these are the important mathematical tools that we're going to use throughout the definition of door patterns, basically. And the following slides will just start to illustrate door patterns, and hopefully some of you are interested in this. It's actually going to be quite long. In fact, this slideshow, I think, has at least 140 slides already. And then there are 3 complex door patterns: funnel, cave, and vortex. I'll place them at last due to complexity. So hopefully you get used to how the door patterns are going to be defined, and then we can come back to the harder ones. So, and here, make sure you're familiar with the indexing of the third order tensors. Specifically, the Ij really represents Yx, so there you go. The representation of block presence, absence, and the definitions of the functions. So, the indicator functions and the minimum maximum functions. So, yep. So basically that's that. Now we head on to the first pattern. It's nothing that special. It's just regular pattern. We don't really say regular pattern, to be honest. We just say, 3x3 piston door, for example. We don't even mention the word regular. But either way, here it is. So the definition of regular pattern is stated in 3.1.1. Also, by the way, the numberings can change if future updates occur. But then currently, this is the numbering. So for the regular pattern, an m by n door has the regular pattern if the door pattern can be represented by an n by m by 1 third order tensor. Now notice m by n door, n by m by 1 third order tensor P, where Pij1, so ij1 is the entry of the third order tensor P. So make sure you understand that. Where Pij1 is equal to 1 for all I less than or equal to 1 less than or equal to n, and 1 less than or equal to j less than or equal to m. And regular pattern is not really anything that special, to be honest. It's just all ones, which basically means just a flat rectangular area of blocks. So there you go. So yeah, so that's definition 3.1.1. And because this is such an intuitive pattern, I'm not going to give you an example of it. It's just wasting your time. It's just a third order tensor with all entries 1. And because it's only even one layer, so it's just a matrix with all ones. So it's a one matrix, you think of it. So yeah, either way. And then definition 3.3.1. Notice we skipped one index. It's not 3.2.1 because 3.2.1 is funnel. So we're going to skip that. So definition 3.3.1 concerns on the Asdjke pattern. So an n by n door where n is greater than or equal to 2 has the Asdjke pattern if the door pattern can be represented by an n by n by 2 third order tensor P, where Pij1 is equal to the indicator function of I minimum j is odd, and then Pij2 is equal to 1 minus Pij1 for all 1 less than or equal to ij less than or equal to n. So notice the inequality here, 1 less than or equal to ij less than or equal to n. It basically applies individually to both I and j. So it's equivalent to saying 1 less than or equal to I less than or equal to n, and 1 less than or equal to j less than or equal to n. And it's not instead 1 less than or equal to I and 1 less than or equal to I and j less than or equal to n. So make sure that you know that. It's completely different. So yeah, and then let me give you the example. So the 4x4 Asdjke door, can be represented by the following third order tensor P. I usually write it P equals to two matrices, P1 and P2, because I cannot really represent a third order tensor directly. It will require me a 3D graphing stuff, which is probably even more confusing. So I'm just going to use matrices to show you. So P equals, an array of matrices, P1 and P2, where P1 equals to, this matrix, and P2 equals to this matrix. So yeah, basically that. But then probably many of you are going to be freaked out. How do you even know that the matrix looks like this? How? But yeah, either way, I'm just going to leave that out a bit, but then just going to tell you 3x3 to 5x5, the Asdjke door looks like this. So even if you don't know at the end how to conclude the matrices, you can still look at these patterns and try for yourself to generalize the pattern to higher orders. So yeah. And also notice something important is that you have to notice the restrictions, basically. So n by n door. Now, if you remember definition 3.1.1, the regular pattern, it has m by n door. So n by n door really tells you that, hey, the length and the height of the door have to be the same. It has to be a square. If it's rectangle, it's not defined. Okay. Second thing is, there's one thing that says n greater than or equal to 2. So this is also important for, n equals 1. It's not defined. So yeah, there you go. And then I guess another thing important to notice is that, 1 less than or equal to I, j less than or equal to n, these are important because it really tells you the bounds where ij ranges from. So don't try to input anything other than this range, basically. So yeah, there you go. So, after the depiction of this, and before you try to freak out on how you can even derive the matrices and hence the third order tensor, let me just teach you. Don't worry, it's fine. So how to derive? The answer I have for you is to think like a computer, because there's not really any much better way to do things. But either way, let me just describe to you how do you really think like a computer. So the strategy is to use a for loop. If you are more proficient in programming, you will already know what this means. But then if you're not, then let me just explain it to you. So we have two scenarios. Now, the first method is Pijk with case-defined k. So case-defined k, what does it mean? It really tells you, Pij1, Pij2, Pij3, so on and so forth. then we use this method. So for each k that ranges from 1 to L, so we assume is an n by m by L third order tensor. So for each k, basically, then we fix k. So here we, for example, we consider first k equals 1 first. So we fix k equals 1, and then we move on to the second line. For I equals 1 to n, so again, we fix I equals 1 first. And then we move on to the next line. For j equals 1 to m, so we fix j equals 1 first. And if all the statements and conditions are true, then we return 1, else we return 0. So that's just basically applying the indicator function. And then we did it. We did it for k equals 1, I equals 1, j equals 1. But then this is a for loop. So we haven't really finished all our tasks yet. We have to continue. So what's next of j equals 1? That's j equals 2. So for k equals 1, I equals 1, j equals 2, we again consider if all statements and conditions are true. And then we return 1 and return 0. Yeah. And then after j equals 2, we consider j equals 3. And then we just repeat again until we reach j equals m. And then once we deduce that, then the for loop of j equals 1 to m ends. And then we have to loop I now. So what's next of I equals 1? That's I equals 2. So k equals 1, I equals 2, j equals 1, repeat again. And then j equals 2, repeat again, 3, 4 to m. And after m, we completed the for loop for j, but we still haven't completed the for loop for I, because we are still I equals 2. So I equals 3. And then repeat the for loop for j again, 1, 2, 3 to m. And then after that, I from 3 to 4. And then all the way up to n, basically. And then once we really completed all of the loops in I, there's still k. So we need to consider all cases of k. So k equals 1, now we consider k equals 2. And then we do it all over again. So I equals 1, j equals 1, and then j equals 2, 3, 4 to m. And then now I can go from 1 to 2, and then j equals 1, 2, 3 to m, and then 3, I equals 3, and then j equals 1, 2, 3 to m, so on and so forth. Until we completed all the loops for j and all the loops for I. And we're done. When we completed all the loops for k. So yeah. So that's the concept of for loop. It has to do all the things that the value matches, basically. So yeah. So that's for loop explained. And now the second method is actually quite similar. It just tells you Pijk with k in the equation. And this is actually quite similar. It's just switching some indexes. For I equals 1, and then for to n, and for j equals 1 to m, and then if all conditions satisfied, because usually there are going to be some inequalities, then we return 1 for all solutions k, because k is going to be an equation of I and j, and else we're just going to return 0 for all non-solutions k. But then if the conditions are not satisfied, if at least one condition is not satisfied, then we return 0 as always. So yeah, so that's it. And then again, it's just a for loop. And here you can actually swap I and j if it's more convenient, and similar to the first one actually. I won't suggest you swapping k, but then you can actually swap I and j. It doesn't really matter. If it's proved to be more convenient to you, then go ahead, just swap it. Yeah, it still works. So that's how you can think of a computer using for loops. And yeah, it's quite tedious, to be honest. But then, of course, as humans, we are quite smart, hopefully. So yeah, you can probably see which values of Asdjke can make the indicator function be true. Or I should say, let the indicator function be equal to 1. And hence the statement inside is true. As humans, we probably can deduce it better than how machines deduce it, like a for loop. If you're not that intelligent, you can, really try to consider all values of Asdjke, just go on and on and on. But then if you're smarter, probably you can already see some key things that tells you whether the statement is going to be true or false. So yeah. So that's that. Now let's just perform this for Asdjke real quick. So Asdjke, we use method 1. The reason is we write it as Pij1 and Pij2. So it's really case defined for k. So when k equals 1, and we loop it, I equals 1, j equals 1, 2, 3, and 4 will result in odd I minimum j, because I is at its minimum value. So how could j be at least smaller than I? So j equals 1 to 4 can result in odd I minimum j. I equals 2, then only j equals 1, because j equals 1 will result in 1 for minimum ij. But then I equals 2, then no matter what j is, 2, 3, 4, it will still be even. So odd I minimum j. I equals 3. Then we repeat it again. We can see j equals 1, 3, and 4 will result in the odd I minimum j. And then I equals 4, then j is just 1, 3. And then, guess what? K equals 2, do we really need to repeat? No. Because we say Pij2 is equal to 1 minus Pij1. What does it mean? It's just flipping between 1 and 0. So get smarter, I guess. We don't have to repeat this entire process for k equals 2, because once we use k equals 1, then just flipping between 1 and 0, and you immediately get Pij2. So yeah. So that's how you deduce the pattern, and now we go on to corner pattern. I'm not going to repeat that much. I'm just going to give you the important notes of it starting from now. So first off is n by n. So m has to equal to n again. Second one, n larger than or equal to 2. Third one, the third order tensor is of size n by n by n. Okay, that also means that Asdjke is between 1 and n. The fourth one is the indicator function looks like this. So n minus maximum of I and j plus 1 equals k. So that's the important things that you have to notice, like the sentence structure that connects these stuff doesn't really matter. All you need to know is that the mathematical stuff, n by n, n greater than or equal to 2, n by n, the expression of Pijk, and also the bounds for Asdjke. So that's that. Pop quiz. Which method? I'll give you a few seconds. The answer is quite simple. This is method 2, because we say it's a function of I and j, and then it's equal to k. And this is definitely not case defined for k. If it's case defined for k, you will see Pij1, Pij2, but then here is just Pijk, and it's just a general equation for k. So method 2, of course. So yeah. And the example, so just illustrating you what a corner door looks like. So by the way, P1 is going to be the first layer. So the frontmost layer you can think of. P2 is just the layer at the back, and then P3 at the layer at the back, and P4. So it looks like this. And then if you really still can't get a good picture, a Minecraft screenshot will probably help. So here illustrates 3x3 to 5x5. So it looks something like this. And the 4x4, the example one is shown on the top right hand corner. So yeah. So that's the definition of corner door. And then related to the corner door is double cave corner. So again, important things to notice, n by n greater than or equal to 2. The size of the third order tensor is n by n by n. Pijk, the expression, is a bit more complicated. It has an inequality, ij less than or equal to n plus 1. And then an equation of k. So I plus j minus 1 equals k. So that's the first indicator function. The second indicator function, I plus j bigger than n plus 1. So it's just basically the reverse of the first indicator function. And you can also rewrite it as I plus j plus 1 greater than or equal to n plus 1. So I plus j greater than or equal to n. Because I and j and n are all natural numbers. So yeah. And the equation up behind, 2n minus I minus j plus 1 equals k. For all 1 less than or equal to Asdjke less than or equal to n. So that's the double cave corner pattern. I wrote at the front as dual cave corner. I'll fix that a bit later, but it's not really that. It doesn't really matter that much. We usually write it as double cave corner, not confuse with the dual transformation. So that's why I use double cave corner. But then both names are accepted, to be honest. So you can have dual cave corner. Doesn't really make sense, but then yeah, it can be. So yeah. And example 3.6.2 is just depiction of the 4x4 double cave corner door. So it is what it looks like, basically. So yeah. And then 3x3 to 5x5, it looks something like this. So it's a really special pattern, I guess. And then now go play button. This is a bit special. First of all, n by n. So m has to be equal to n again. Second thing, 3 less than or equal to n less than or equal to 5. It's not n larger than or equal to something. It has an upper bound. So yeah, make sure you notice that. It only defines for 3x3, 4x4, and 5x5, really. And then the third order tensor is n by n by 2, the size of it. And then the indicator function, we first define peterjiangTW first. Notice that. And then it's all inequalities. There are no equalities here. And then peterj1 is literally just flipping between 1 and 0. So 1 minus peterj2. And then the bounds, 1 less than or equal to I, j less than or equal to n. Yeah, nothing really special. And also the bounds is, always related to the size of the third order tensor, of course. So it's nothing really special. 4x4, go play button door, just plug the values in and just see how it goes. And it looks like this. So yeah. And then some screenshots for you. So for 3x3 and 5x5. So yeah. And if you really want to try, you can try plugging in, n greater than 5 really, but then it's not defined basically. But then the analytical continuation can still make sense, I guess. Although we don't recognize it, at least here. So yeah. 3.9.1 is on pitch. Now this time is m by n, so m can be different than n, where m and n are both greater than or equal to 2, has the pitch pattern. If the door pattern can be represented by n by m by n, third order tensor p, where peterjk equals, it's just a simple function, n minus I plus 1 equals k. For all ik in 1 and n inclusive, and j in 1 and m inclusive. Notice j doesn't even depend in the indicator function, although we still have to bound for j because we cannot accept j as some non-accepted values. So, and plug in the values. It's just basically a bunch of rows of ones. Yeah, it looks like this. So yeah. And then if you really want some Minecraft screenshots, here's 3x3 to 5x5. It's just like a staircase to top. Block staircase to top. This is how the pitch pattern is basically defined. So yeah. Bar pattern is very close to its neighbor pitch, although a bit different. So once again, something's important to notice. M by n. Mn bigger than or equal to 3 this time. The third order tensor size is n by m by ceiling function of 0.5n. If you don't know what a ceiling function is, well, basically imagine any decimal number and then round it round up. Yeah, that's how we call it, round up. Round up your decimal number, and that's basically the ceiling function. That's it, nothing much. And for integers, of course, you don't. Rounding up an integer gives you the exact same integer. So, Pijk, the function expression is I equals k, or n minus I plus 1 equals k. So you can see the relationship between bar pattern and pitch pattern. N minus I plus 1 equals k are both in it. But then now, for the bar pattern, it has I equals k as well. The most different thing, perhaps, is that the bounds of k. Because the bounds of k is no longer 1 and n inclusive. It's 1 and ceiling of 0.5n. So that's the difference. So basically, it's going to be chopped off halfway. So the bounds in full is I in 1n inclusive, j in 1m inclusive, k in 1 ceiling 0.5n inclusive. So yeah. The example looks like this. I use a 5x3. So yep, it looks like this. Again, a bunch of rows of 1, but then this time the bunch of rows of 1 can be 2 in a layer. 3x3 to 5x5 looks like this. And yeah. And then we move on. Now, red bars, spooky. Now, the following 3 patterns will always have this red bar here because we are talking about the regular arrangement. So, yeah. So we're entering the territory of section 2.1 BII. So the previous stuff are about section 2.1 BI, but then here is section 2.1 BII. And since it's BII, we have to mention the arrangements of the pattern because this is the composition. And the arrangement, as I've already said, I'm just going to mention the regular arrangement. So 3.11.1 definition. Sissy bar, what things are important? M by n. M doesn't have to be equal to n. Mn bigger than or equal to 3. And the third order tensor pattern, the size is n by m by 1. Pij 1, because there are no varying values of k, it's just 1. So there are 2 indicators. One is I less than or equal to 0.5n, then I is even. The second one is I greater than 0.5n, n minus 1. So n minus I plus 1 is even. So, and then the bounds of I is 1 and n inclusive, bounds of j is 1 and m inclusive. Now, the example is a bit special. I use a 3x10 Sissy Bar door. And I forgot to change from bar door to Sissy Bar door. Must be because of my copy and pasting not being careful. But either way, the 3x10 Sissy Bar door represented by the following third order tensor looks like this. So yeah. I'm not going to give you any screenshot of it. Cut me some slack because the patterns are all already depicted in screenshots in the regulations documents already. So for any of the patterns that I don't give any screenshot of it because they're all given in the regulations documents already. So yeah, there you go. So yeah. I want to be lazy. Okay, checkerboard. Again, regular arrangement assumptions. So there you go. The pattern what things are important. M by n. M doesn't have to be equal to n. Mn or greater than or equal to 2. Third order tensor size, n times m times 1. And then the indicator function, I plus j is even. Yeah, very simple. And then the bounds of I, 1 and n inclusive. Bounds of j, 1 and m inclusive. So, yeah. And then 4x4 checkerboard door, just a bunch of crosses, guess you can say. Then 3x3 to 5x5 looks like this. And also, I guess this is also important to notice is that checkerboard pattern really looks like this for 3x3 and 5x5. Don't invert it. So don't have the zeros as ones and don't have the ones as zeros. It's important that it looks like this. Otherwise, it's a different pattern, which is actually not even defined. So yeah, either way. The last one in section 2.1 BII is the full checkerboard. The one that I said is not really in the documents, but we commonly accept that it is. So it's very similar. M by n. M doesn't have to be equal to n. Mn greater than or equal to 2. N by m by 2. This time, not 1, it's 2. So Pij1 is still I plus j is even for the indicator function. And then we have Pij2. It's literally just flipping between 0 and 1. So 1 minus Pij1. The bounds are the same. I is in 1 and n inclusive. J is in 1 and m inclusive. I have already said it. Although the regulations document doesn't mention the full checkerboard pattern door, it's commonly agreed that this is still a valid door pattern. So, example, P1 still the same. P2 is just the invert of it. Looks like this. So, 4 3x3 to 5x5, and yeah. Now, all the door patterns in section 2.1 BII are all talked about, and guess what that means? We are going to talk about the 3 most complex patterns ever to be defined in this document. They are funnel, cave, and vortex. So yeah, I have to really give this complexity alert because it's really complicated and probably going to scare most of you. Because one cannot really imagine just how difficult the definition can be to understand. And it really requires me to explain to you throughout. So yeah, I'll give you a detailed explanation rather than just showing you the example and then we move on like that. I really will derive the matrix with you alongside. So, funnel. The important things, m by n doesn't have to be equal. Mn or greater than or equal to 3. Size of the tensor is n by m by ceiling of 0.5 times the minimum of m and n, where Pijk has 4 terms, each connected with an OR gate, and each of the terms have 2 inequalities and 1 equality connected all by AND gates. I'm not going to read all of them out. It's too demanding. And then the bounds, I is in 1 and n inclusive, j is in 1 and m inclusive, k is in 1 and ceiling of 0.5, minimum mn inclusive. So yeah, get used to complex expressions, I guess. This is already by far the easier ones, to be honest. It's not really that bad, to be honest. Like, if I just show you each one of them separately, it probably doesn't feel as bad. And then I'll give you an example. 7x5 funnel door. I give you a large door example because I really want to illustrate to you how we can derive things like this. And giving you a large example is also good just to sanity check if the definition makes sense. And give you a full context of it. So, 7x5 basically that means m is equal to 7 and n equals to 5. So we just replace a bunch of stuff that we already know, and it looks something like this. I'm not going to include the bounds, I in 1n inclusive, j in 1m inclusive. Those bounds I'm just going to skip. I assume that everyone knows it. So yeah. So now we're going to derive the third order tensor, that represents the 7/5 final door. And it looks something like this for the indicator function. And then we can simplify it. So from here, like the second indicator, or I should say the second statement, I plus 7 greater than or equal to j plus 5. We can simplify it, and like many others as well. So it looks something like this. And then here I want to do a visual illustration. I'll color things. Ooh, so colorful. And then what I'm going to do is plug in decimals and give you the ranges. And it looks something like this. So it's actually, so hopefully you really know what the bounds are really trying to do, basically. So the red bound corresponds to the red region, blue bound corresponds to the blue region. You know the gist of it. Now, if you really plug this in decimals, you're not going to see the same results. That's because, for example, the red region. The red region looks like, what do you call it? A trapezoid. But then the bounds it gives you really gives a triangle instead. It doesn't give you a trapezoid. So why is it a trapezoid? Well, remember the bounds of I, j, and k. We have to apply these bounds to here as well. So that's why it looks like a trapezoid. And similarly for the blue region. And then for the green and orange, they really look like this. Okay. They really look like triangles. So yeah, that basically represents that what each of the statement is concerning about the values of I, j, and k. So the area that they are affecting, basically. So yeah. Okay, so next we use method 2 because Pijk is not Pij1, not Pij2, it's Pijk. Okay, so we consider the first indicator. So I equals k and blah, blah, blah. Yeah, whatever. So when I equals 1, k has to be equal to 1 in order for the statement to be true. And then, we have the two inequalities. So 1 less than or equal to I, 1 is less than or equal to j, and 1 plus j less than or equal to 8, which implies j less than or equal to 7. But then, remember, we have j is in the bounds of 1 and m. So really, it's 1 and 7 now. So j is in 1 and 7 inclusive. So yeah. I is equal to 2, then use intelligence. K is equal to 2. Only this can be true. 2 is less than or equal to j, and 2 plus j less than or equal to 8. Combine these, 2 less than or equal to j less than or equal to 6. I equals 3, k equals 3. Again, plug in the values of I and give you the bounds of j. And then we know that when I equals 1, 2, 3, k equals 1, 2, 3, the corresponding of what j is going to be such that the statement is true. So, and then finally, I cannot be greater than or equal to 4. K is 3 at maximum, remember. So, yeah. We don't have to consider values of I greater than or equal to 4 at this time. It's just all going to be 0. K cannot be equal to 4, 5, 6. Whatever. No. So that's, therefore, this part of the indicator can only be true when ijk is in these values. So we can just list them out. So I equals 1, then you just permutate j, so 1, 2, 3, 4, 5, 6, 7, and then I equals 2, k equals 2, and then j equals 2, 3, 4, 5, 6, and then j equals 3, 4, 5, for I, k equals 3. And then we do this a bunch of times. We just need to do this 3 more times. The second indicator function. So again, method 2. I cannot be less than or equal to k is 3 at maximum. So that's important. I equals 3, k equals 3, plug in the values, gives you j is in 3 and 5 inclusive. I equals 4, k equals 2 this time, because it's 6 minus I equals k. So j is between 2 and 6 inclusive. I equals 5, k equals 1, plug in for j, 1, 7 inclusive. And then I just permutate it for all values of j, so 511, 521, blah, 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 blah. So, third indicator. This time is better for us to fix j and then permutate I. J equals 1, k equals 1, plug in the values for j. I would be in 1 and 5. J equals 2, k equals 2. I would be in 2 and 4 inclusive. J equals 3, k equals 3. I can only be equal to 3. J cannot be larger than or equal to 4 because k is at maximum 3. So Asdjke is in D such that the indicator is true. This part at least. Finally, for the last indicator, method 2, j cannot be less than or equal to 4 because k is 3 at maximum. Then j equals 5, k equals 3, this time 8 minus j equals k. So plug in for I can only be 3. And then j equals 6, k equals 2, I is in 2, 4 inclusive. J equals 7, k equals 1, I is in 1 to 5 inclusive. Then Asdjke looks like this. And finally, using all of the results that we have, combine them and look a bunch of things like this. Don't worry, simplify it and order them nicely, basically. And it looks something like this. And if we want to depict it using matrices for all the tensors, it looks like this. So it's just a ring and a ring and a ring of blocks. And that is the funnel pattern. Yeah. So much complexity just to give you a pattern that has rings. Math is fun. So that's how you really define a complex pattern. Hopefully you understand the procedure much better now. Cave pattern. Yeah, it's going to be worse from here. Important things. M times m. M times n. So they don't have to be equal. Mn greater than or equal to 3. The third order tensor has the integrator function in it. So n times m times minimum of mn minus that if it is equal. That is even, then you need to minus 1. So yeah. And then the third order tensor where, a bunch of stuff. So the first 4 looks quite similar to each other. And then the last 2 are basically some special considerations. And the last 2 are here actually. I cannot even include everything in one single slide. So yeah, the last 2 parts of the indicator function is here. So yeah, the last 2 conditions are they're mutually exclusive, first of all, because we have m greater than n versus m less than n. So yeah, mutually exclusive. The second thing, it resembles the bar pattern, actually. And if you recall it, bar pattern has I equals k or n minus I plus 1 equals k. And here we really see that resemblance here as well. Because guess what? The bar pattern can also be replaced with minimum of I and n minus I plus 1 actually. It's just I don't use that there. But here, I have to use it for reducing complexity. But then it just adds, it's a ceiling of 0.5 and, and -1. Yeah, it's just a bunch of stuff. Yeah. So yeah, just a bunch of equality mess. So yeah. So that's that. And then now we're going to move on to examine example 3.4.2 on the 7x5 cave door. And yeah, plugging the values m equals 7, n equals 5 into the definition of cave door, we get, first off, the third order tensor has 5 matrices. And then, a bunch of inequalities here and here. Oh, actually, the entire thing can be constricted down to this here. Now, if you look a bit closer to what's the last condition, 7 less than 5. This is false, definitely. So the entire thing can be thrown out. This is always false because we are connecting it with AND gates. So we can throw out the last condition, and the remaining conditions we can just simplify it because the ceiling functions, the floor functions, they can all be evaluated now because we have the values of m and n. Looks like this. This looks very clean, actually, to be honest. Like, if you look at it right now. Like, before, it looks like a mess. But then, after you plug in the values of it, it looks so clean and it really has a structure, to be honest. And then, color code it. Plug it in Desmos, looks like this. It looks really nice. It's just basically a bunch of square regions and a rectangular region in the middle. And the rectangular region is represented by the last indicator function. Because the last indicator function is doing something very special. It's doing a bar pattern, as I said. The remaining ones, they are doing something entirely different. But the last one is just basically a bar pattern. So yeah. And the regions that they're controlling, they're affecting, is basically shown in the Desmos graph shown below. So, it looks really nice to finally see something, from that complexity reduced down to just a bunch of square regions. So yeah. Anyway, so now we're just going to divide every single 5 of the indicator function parts, and then just consider them individually. I'm not going to spend you another 10 minutes talking about how we derive it, so just going to skip you to the results. So Asdjke is in these. Verify it yourself if you really need to. And to be honest, this time is already simpler because it's really a square and a square and a square and a square and a rectangle, I guess, also region. So you can really make sure that you don't get your inequalities wrong, because you don't have to even consider inequalities now. It's given to you. So just plug in the value, see whether they're true or not, and then just give you functions like this. You don't even need to see they're true or not, because I and j permutate from 1 to 3. They can each give you a value of k that is valid, to be honest. And then same for here, here, here. The last one, I will tell you how to derive it, because it's entirely different. So I equals 1, k equals 3, and then j, the bounds are always 3 and 5 inclusive, and then I equals 2, then k equals 4, I equals 3, then k equals 5, I equals 4, and k equals 4, I equals 5, and k equals 3, and then just say a bunch of Asdjkes where the indicator function will be true for this part. And then lastly, plug them in. We created a bunch of mess again. It's fine. I'll help you to clean it down to something like this. It looks really neat again. But then this time, the matrix depiction of it looks quite ugly. you might not really know what it's trying to do. It looks like something like this, and then something like this. And yeah, P5 has to be in this slide because I cannot show you every single matrix in one slide again. So yeah, but yeah, either way, cave door, I think the screenshots are already in the regulation document. So yeah, I'm not going to provide it here. If you really want to see how the cave door looks like, how you can expand it without deriving these matrices, just look at the screenshots in the regulation document. So yeah, the last one is the hardest one, Vortex. And yeah, mention something. First off, n by n. Yeah, m has to be equal to n. So you don't have another variable m. Congratulations. Although the pattern is more complex to the point it's not congratulating you. N is greater than or equal to 4. Yeah, this is quite a bit special. Mostly it's going to be greater than or equal to 3, or 2. But then this is n greater than or equal to 4. Because if you're trying for n equals 3, I'll tell you there's actually n equals 3, but it's just not defined here. N equals 2, what are you trying to do? Say, yeah. Vortex pattern, and the third order tensor size is actually quite simple, n by ceiling of 0.5n. Where, yeah, this part gets a bit crazy. So we have a bunch of indicator functions, or an indicator function mass, and then minus indicator functions, 4 of them. You really haven't seen much of minusing indicator functions. Well, I mean, you have seen it in the cave door one, but it's just only regarding on the size of the third order tensor. But then indicator functions subtraction in Pijk. That's the first time you ever see that. And probably the only time you'll see it, to be honest. Yes, Vortex pattern is so unintuitive, it requires subtraction of indicator functions. Don't worry, I'll tell you what it really means a bit later. And then, oh yeah, we also add 8 more indicator functions. So yeah, unfortunately. So yeah, not only do you have one indicator function of a bunch of mess, you need to subtract 4 indicator functions, confusing enough, and then add 8 more. So yeah, the bounds are quite simple though. Ij in 1n inclusive, k in 1n ceiling of 0.5n inclusive. So yeah, the nightmare of all door patterns has to come down to Vortex. And hopefully this doesn't scare you away yet. Not like the other two haven't scared you away already. Either way, so we still have to face our example. I'll use a 7x7 Vortex door. So plug in the values of n to here, and then you can simplify down a lot of things already. Then we have this here and this here. And then here, I didn't cover the first part because I'll explain what the first part is. I'm just going to cover the subtractions of the indicator functions. And honestly, they're not that bad. Once you plug in the values, it doesn't look so bad. And then you can just find the values and satisfy it. In fact, there are only very few of them, to be honest, because it's I equals something j equals something k. So you really don't have much numbers that can satisfy them. And once you fix a certain number, you can already fix other numbers. See? And here it's best for you to fix k. And then just find values of I and j. And then, oh, another mistake I haven't, that's not a minus sign, that's a plus sign, unfortunately. So I'll need to change that. So the second one, use method to get something like these. Again, because it's the same story as the previous subtraction of indicators. So once you fix one of ij or k, you can find the values of the other two variables. So yeah, it's not that much. Again, here it's best for you to get k because k's can only be from 2 to 4 inclusive. So. And the third one, it's the same story once over again. This time it even reduces you to k equals 2 and 3 only. So yeah. And then we can just include it to here and here like so. And now here comes the explanation part. Notice the first part of the indicator function is what defines the funnel pattern. Yes, vortex pattern is dependent on the funnel pattern. This is probably an easier way to explain to you how to make a vortex pattern. So yeah, so if you know how to make a funnel pattern for the 7x7 funnel door, you know how to derive the first part of the indicator function already, which is probably not less demanding than any of the others, to be honest. And now, the second thing is that the subtraction of indicator function basically just represents turning the corresponding blocks from door blocks to air blocks, because we are always subtracting 1 if the indicator function is true, has a true statement. So yeah, just turning from door blocks to air blocks. And the addition of indicator function represents turning the corresponding blocks from air blocks to door blocks. You already seen it actually in some other patterns. So after all those addition and subtraction, I'm going to skip the details. We obtain this expression, and it looks not that intuitive for matrices, perhaps because there are a bunch of zeros, to be honest. So you don't really see what's going on, but then later I'll have screenshots of it, don't worry. So yeah, we obtain the following expression of P. It looks something like this, and it's actually like a turbine, somewhat. So yeah. Now, how to understand the vortex pattern definition? As I've already said, it's just a modification of funnel pattern. And take the indicator functions from the 7x7 vortex door. Step 1, set up the vortex as the funnel pattern, and it looks like this. Step 2, we remove specified blocks, and from here, the first picture, we go on to the second picture, which looks like this. So if you cannot see the gist of it, it's just basically removing a line of blocks. And each line only has 3 blocks removed. Step 3, adding back the blocks that we have removed, but 1 block backwards in terms of the layer. And it looks something like this. It still looks broken. So, step 4, make it such that we cannot see the other side. There are no holes. So yeah, so that's how we can understand vortex pattern. If you want to make it by hand, I suggest you start off with a funnel, remove those blocks, push them to the back, and then add back some blocks that, such that the pattern has no holes. So yeah, so that's how you get the intuition of vortex pattern, according to the definition at least. So yeah, so that's that. Vortex hasn't ended. 3x3 exists. Well, we can define vortex pattern for 3x3, but the definition is a bit different actually. So because we are only defining on one specific size, so we can really just say stuff like this. And then the example is literally just the only example that can illustrate the definition. And it looks something like this. So for 3x3 and 5x5, it looks like this. And yeah, alert, vortex pattern is defined differently for 3x3 and 4x4 and above. Do not mix them up. So don't try to apply 3x3 apply 3 to the general definition and I don't know how you can apply 4 by 4 according to the horizontal vortex door pattern. I don't know, but then in case if you know how to do that, don't do that. So yeah, either way. So this is how the 3 by 3 and 5 by 5 looks like. So yeah, the 3 by 3 is just like completely different from the 4 by 4 and their counterparts. So yeah, it's quite funny to be honest. So yeah, so that's the visual example of the vortex pattern. And before I move on to discussing section 2.1 BI on the transformation of door patterns, I want to talk about how you can visualize door patterns. Because after all, looking at the definition of door patterns, yeah, we really do consolidate the definition of terminologies. But what use of it could it bring other than just simply a definition? Well, we can visualize it to give it more of a meaning. So yeah, unfortunately, visualizing has one drawback, is that we cannot really visualize it much for door patterns with case-defined K, or door patterns that are too exotic, like the Vortex door pattern that subtracts indicator functions. You see, subtracting indicator functions, that's not a good sign. So don't try to visualize a Vortex door pattern. It's just too much. It needs to subtract all those blocks and then add back all those blocks. So basically, you need a bunch of lines just to illustrate it, and then it just beats the whole purpose of visualizing. It just makes it more confusing already. So don't do that. Know how the funnel pattern works, and then just alter it to make the vortex pattern. It's already good enough for you. But yeah. But then, for some nice patterns, so basically door patterns with indicator functions not case defined for K and except the vortex pattern, we can visualize the door pattern in a 3D graphing calculator. And here I'm going to use Desmos. Here's the link. It's 3D one. It's not the normal graphing one. So yeah, make sure you know that. So we take the funnel door as an example. We call the indicator function looks like this. Not going to repeat that again. Step 1. For the indicator functions with logic OR, simply replace them with the addition of indicator functions. Now, this is not mathematically correct because there are some overlapping door blocks, and then you will get an indicator function with you get peterjiangTW with a value greater than 1, which is not defined. But then don't worry, we are not trying to deduce the value of peterjiangTW. We're just trying to visualize the door pattern. So it doesn't really hurt. And in fact, it won't affect the graphing results because they are ORs. So any value greater than 1 just basically still is 1. To be honest, the block is still here. It doesn't duplicate the block in a visual graph. So don't worry about it. So yeah, it won't affect the graphing result. Trust me on that one. Step 2. Now, remember that I represents the y-axis, J represents the x-axis, K represents the z-axis. Replace that with these. And it looks like this. Step 3. Flashbang with Desmos. In Desmos, add 2 sliders for M and N. This is, just setting up stuff. So I here set M equals 5 and N equals 3. But then you can set any value. You can even change it after that. Just don't get decimal values. I don't know what that will give you. It will probably be something very funny. Yeah, either way. Step 4. For each indicator function, we add a new graph, or I should say a new equation, and type the equality part first. And if there are no equalities, then just type any inequality as the equation. I'll use the first indicator function first. So y equals z, and y let's say equals to x, and y plus x let's say equals to m plus 1. What is the equality part? Is y equals z. So I type in y equals z into here, and it looks something like this. Step 5. add the inequalities of the indicator function after the equation. So the inequalities of the first indicator function is y less than or equal to x and y plus x less than or equal to n plus 1. So I just add them in the back. And the format looks like this. So just have a set of braces including each of the inequality. So, and you can also see it in the graph actually. And it looks something a bit weirder now, but don't worry, we'll fix that a bit later. Step 6. Guess what? We haven't finished adding our restrictions. We also have to add the restrictions that comes itself from the size of the third order tensor, of course. So with the funnel pattern, what is the restriction? Is y is bounded by 1 and n inclusive, x is bounded by 1 and m inclusive, z is bounded by 1 and ceiling function of 0.5 times the minimum of m and n. So in case if you don't know the format, so here I show you again. Ceiling function is CEIL, and then small brackets and then a bunch of stuff. And then minimum of m and n is just minimum of braces m, comma, n. It really is how we write it mathematically as well. And then for the floor function, it's just typing floor instead of ceiling, or I should say seal. So, and then it looks something like this. It looks like a triangle now. It looks nice actually. Oh, actually, step 6, the graph is incorrect. I mistyped. I think. Yeah, I mistyped somewhere, but then I don't know where I mistyped. Either way. So, yeah, anyways, so step 7, we repeat steps 4 to 6 for each indicator function until all of the indicator functions are considered. So, yep. And then you have the entire pattern, and guess what? You're done already. Just move around. And also a note, if you want to see the pattern from the front view, you have to look towards the positive Z direction. So you basically have to flip the entire thing such that, you know, the Z is pointing downwards. So it's not that great of a view, to be honest. But then either way, that's how you can look at the front view for yourself. So yeah, that's how you visualize door patterns basically. So yeah, that's the end of the visualizing door pattern part. And now we're going to talk about the transformations. It shouldn't be that long, to be honest. Now, just some notes for you, because the document isn't to fully reconcile the regulations document, but it does provide some important and useful definitions of door patterns. But then in the other parts of the document, it tries to expand on the idea of regulations towards other stuff. So it does include some hypothetical regulations for door pattern transformations, and they do not follow the regulations. So I'm going to skip the discussion of hypothetical regulations and only mention the definitions of existing transformations. Yes, there are also transformations that did not exist, and they are also included in the document. So yeah, you'll see what I mean when you actually look at the document yourself. And for interested viewers on the hypothetical regulations, you just check out the documents, and hopefully you understand what I mean by those. It's not too hard to understand, to be honest, because they're mostly verbal, not a bunch of mathematical expressions. But yeah, either way. So definition 4.1 is vertical, and I'm going to talk about how the document defines transformations versus how the regulation document defines transformations. So vertical, a vertical door pattern represented by the size of a tensor is the 90-degree clockwise rotation of door pattern, represented by an m by n by l third order tensor P. So you see the sizes change differently, such that Qijk equals Pj n minus I plus 1, k, for all those bounds. Yeah. Now, compared to the regulation document, the definition of vertical is the type is rotated 90 degrees, and they only apply to 3 patterns: bar, glass stripe, the thing that I didn't cover this time, and pitch. And vertical pitch is equivalent to yaw door, so which I also mentioned here. 3x5 yaw door, equivalent to the 3x5 vertical pitch door, can be represented by the following third order tensor. And remember that we already talked about the 5x3 pitch door, and the 3x5 yaw door is just basically the vertical transformation of the 5x3 pitch door. And also adding a remark, although the original pattern is a 5x3 pitch door, the size name of piston door follows the piston door size after transformations. So don't call it a 5x3 vertical pitch door, call it a 3x5 vertical pitch door. So it's instead called a 3x5 vertical pitch door, or in this case, there's a special name for it, 3x5 yaw door. So yeah. I didn't include this example in the documents, but then it's important for me to include it here because we are talking about the regulation document. So the additional example concerns on the 3x3 vertical vortex door, which is basically the vertical transformation of the 3x3 horizontal vortex door. And it looks something like this. And yeah, needless to mention, although the regulations document does not mention the vertical transformation that apply for vortex, but then it's commonly agreed that the 3x3 vortex door, the vertical transformation does apply to this door, but not for any doors 4x4 plus. It's important that you know this. It's only for 3x3. This is a special case. Very special case indeed. Because 3x3 vortex door is such a weird door. It does have to be defined separately. And the regulation document didn't consider this much. So we have to notice that here. So yeah. Okay, so now we move on to another definition, reversed. It's just basically the 180-degree clockwise rotation, and then the third order tensor sizes are the same actually, such that Qijk equals p n minus 1 plus n minus I plus 1 m minus j plus 1 k for all bounds. And then compared to the definition of reverse from the regulations document, the type is rotated at 180 degrees, only applies to pitch. So yeah, again, important thing, only applies to pitch. And then, because it only applies to pitch, the example is only considered on pitch as well. 5x3 reverse pitch door, 180-degree rotation. What does that look like? It looks like this. So yeah. And then lastly, we are going to cover on definition 4.8, inverted. So yeah, the tensor size is the same. And then Pijk equals Qij. This time it's only the k that changes. L minus k plus 1. And then for all bounds. Nothing much. And then definition of inverted according to the regulation document is this. The type is flipped front to back. Only applies to funnel. So yeah, that's that. And then here's the example of this. So because it only applies to funnel, so I just give you a funnel example like this. So it looks like this. Nothing that much. It's just P1 and P2 swapped from the original pattern. So, and also, I guess I should also mention this is the history on why vertical, reversed, and inverted only applies to these door patterns. It's from the synergy world records plot. Basically, these are the categories that they place inside the plot, and then because this plot has significant impact over the regulations documents, and at that time, because we have these transformations, but we don't want to apply the transformations to all patterns yet. So we are only applied these transformations to certain patterns, and these patterns are according to what the world record plot has, and hence, yeah, it stays up till now. And another history and the fun fact is that I previously did propose to remove these stuff, but then at that time it doesn't have a consensus yet. So I'm not sure now if it has any consensus, but yeah, it's not that important to me anyways for the proposal. So yeah, let's just get left step. So yeah, that's also some history on why the transformations only applies to those patterns. And if you're interested in how transformations can be proposed to generalize to all patterns, please refer to my document. It does give you some really surprising results, I guess. Yeah, that mentions what restrictions we should put to door patterns such that they can be eligible or not eligible to certain transformations, basically. So yeah, but otherwise, thank you for watching this video. And yeah, I'm not going to go back to the PowerPoint already. Just going to end here. And yeah, hopefully you learn more about door pattern and specifically their definitions, I guess. So yeah, and if things work out, part 2 will come out. If things don't, it won't. So yeah, anyways, I'll see you in the next video.